Welcome to the AstroAI meeting delayed by talk delayed by 1 day because of the snow. I am very happy to have Mikaeel Yunus from Johns Hopkins University SDSS, where he works with John Wu. We didn't meet him this morning, but we actually crossed paths at the NeurIPS conference in December, but we didn't get a chance to talk. And he's he's a 4-year grad student there, and he's going to be telling us about some really interesting work about how you do inference on galaxy properties with probabilistic methods when you only have the galaxy image rather than a spectrum. So the floor is yours. This is intended to be very, open. So please interrupt with questions, and the floor is yours for the next 4 minutes or so. So please take it on.
Thank you very much. Hi, everyone.
Oh, sorry.
Oh,
Mikaeel is here for at least part of this week.
Yes.
He's going to be sitting in D304. So if people are interested in chatting with him, please just reach out or go to that.
literally break down my door. I'll be there. Yeah, hi, everybody. My name is Mikaeel, as Raphael said. I am a 4th-year grad student at Hopkins, and thank you all so much for coming out here in the snow. It really means a lot. I'm very grateful. So my work mainly has to do with machine learning applications to galaxy physics, where they're pretty nearby galaxies, pretty low redshift. And I'll get more into that in a bit. And again, please interrupt questions as I go. Okay, so to sort of motivate this work and talk about the problem that I eventually want to attack, the dust stage degeneracy, I'll start with this sort of very pedagogical example of photometric SED fitting. So in a case where you don't have full spectra to derive a galaxy's physical properties, like, for example, stellar mass, star formation rate, metallicity, and whatnot. Essentially what you do, you observe the galaxy in a limited number of broad bands, I don't know, like U, G, R, I, Z, some very small set of numbers, and using pick your favorite SED fitting code, Segal, Prospect, or whatever, you fit through those lines, and whatever spectra works the best, those are the properties that you end up going with that generated that model spectra. And this is used because it works. It's pretty effective, but it can run into some pretty hairy issues. So, for example, if you have a old and not dusty galaxy, by the little. Oh, I'm so sorry. I thought I did that.
Yeah.
There we go. Thank you. Sorry. So if you have an old and not dusty galaxy, and by dusty I mean dust attenuation, versus a young and dusty galaxy, you can run into an issue where the dust reddens the light in front of the galaxy and makes it look photometrically a lot redder than it actually is. And you can end up deriving 2 very similar sets of galaxy properties for 2 very different galaxies, which is not good. So how do I envision trying to relieve or break this degeneracy? Sorry, this is not okay. I believe in the power of images. Galaxies come in all different shapes and sizes. Spirals, you have bulges and disks, spheroids, whatever you like. And there's so much information packed into these images that is not being leveraged with traditional photometric SED fitting methods that we could be using. For example, if we had a very reddened young and dusty galaxy and then we saw that it had spiral arms, we'd be like, oh yeah, this is probably young and dusty, not an old stellar population. So that's the broad strokes of what I'm trying to do here. So my thesis essentially is that the morphological information contained in images can help us constrain galaxy properties. So for the first part of my talk, this is kind of an extended version of what I gave at AAS. I'm going to be talking about the SDSS main galaxy sample and the work that I did there. And then in the second part of my talk, I'll talk about a different data set. But these are the variables that I'm dealing with: stellar mass, star formation rate, metallicity, DN4000, which I'm just treating as an age proxy, and dust attenuation. So methods and results. To talk about a little bit of, yes, question.
What do you do with the age yet?
Oh, I filter those out. So I'm just doing star formation galaxies that are filtered by like BPC class. So I'm not dealing with AGN yet. That'd be a great future direction though. For the machine learning, I'm using what's called conditional flow matching. For anyone in the room is familiar with things like normalizing flows, anything where you're estimating densities, it works in a very similar way, where you start with here's an animation that I hope works. You basically start with a source distribution, a really uninformed Gaussian, and you're learning this function that takes you from that Gaussian to a target distribution, which is represented by your data. And you're doing that by basically learning this velocity field. So instead of learning a bunch of discrete flow functions that have to be invertible, you're actually learning basically a continuous, like a slope essentially, that you can integrate over. And will continuously transform you from your source distribution to your target distribution. And importantly here, there is, in the version of the algorithm I'm using, there's a time parameter that takes you from the source at t equals 0 to the target at t equals 1. And you can use a conditioning vector and concatenate that to time. And in that conditioning vector, you can put in data about your galaxies that you're looking at. So for example, encoded down galaxy images, photometry, you name it. And that helps basically condition this model. So what I do here, I have two models. One of them I call an image model, where the data I'm conditioning on is both galaxy images and photometry. And then I have a photometry model. It's kind of like my control that doesn't have images in it. It's just the photometry. And my hopeful goal, obviously whatever result comes out, but my hopeful goal is to show that the image model outperforms the photometry model in all these different ways. So how do we evaluate this? The first way we evaluate it is using posterior performance metrics that one of them I kind of homebrewed, delta log P. It's a lot like a Bayes factor, where essentially what you're doing is you take your conditional flow model that you've just trained, you sample from it, pick your favorite number, like 1,000 times, and you create a posterior distribution out of that using some sort of kernel density estimator. And you're basically seeing how close that posterior distribution gets to your spectroscopic targets, which I use ground truth in quotations. It's not like, it's as close as we can get to the ground truth essentially. So that I'm calling an accuracy metric, and then KL divergence, which I'm calling an informativeness metric. So if I'm comparing the posterior in blue to the prior, which I'm just considering to be the entire spectroscopic data set, basically like if you just made a random guess using the data you have, how different is the posterior from the prior? So is it actually doing something to get closer to the truth? So I plot these metrics for the image model I trained versus the photometry model. And I generally get that the image model does better. It's not like a slam dunk, but the delta log P is higher for about 81% of the images, which is nice. And then just for sanity, just to make sure I wasn't getting issues where I had like high delta log P's and low KL divergences, I also made a scatter plot. Checks out. Okay, so moving on to the next slide, oh, sorry, question.
Did you try with images only?
Sorry?
Did you try with images only?
Yes, I did. It was pretty similar actually to the image model, which is interesting. So for this data set I did, but I ended up putting the photometry in the image model so that I'd have a more apples to apples comparison. But it was about as informative as the and accurate as the image plus photometry model. That's a good question though. Yes.
You're not using simulations here. Your ground truth comes from spectroscopic measurements.
Yes.
But how are you getting posteriors for the parameters here through your normalizing flow? So through your flow matching approach. So the distribution you're trying to model is the distribution of the pixel values on the images. Is that correct? Or is your target the posteriors themselves of the parameters? And if that's the case, where does that information come?
So yeah, so my target is I guess the maximum likelihood values of these posteriors. I mean, ideally I would have, so if I go back to something like this, ideally those red points would be entire distributions that I'm comparing to, but I think like storing all of those would be like petabytes of data. So for now, and this is something that I'm thinking about for my future work, for now I am basically, so like you do some sort of spectral fit on your SDSS spectra, and whatever the maximum likelihood properties are that come out of that, those are my targets. But ideally they would be more, which is, by the way, this is the reason I use this like weird delta log p metric. Ideally they would both be distributions and it would be a lot easier to compare them, but I'm comparing a posterior coming out of my model through sampling to a Dirac delta function coming from the spectroscopy.
And just a small follow-up. How do you disentangle your performance in this likelihood landscape? So what you're trying to do here is look at where the ground truth lives with respect to your posterior, right? So
yeah,
as a way to evaluate how well you're doing tonight. But since the ground truth comes from spectroscopic measurements, is there any chance that there might be some bias between the spectroscopic measurement and what you would have gotten from an image that you need to correct for here? How well specified is the ground truth given that it comes from a different sort of measure?
It's a really good question. I think it's something that we have to watch out for. We don't really deal with that yet, but even going between, what I can say is even going between, later I'll talk about, this is all SDSS, but I do the same sort of thing on a DESI decals data set, and it's very different biases. So that's something that we'll have to also think about. And I'm happy to chat more about that later because I'm kind of not really sure what to do there right now. Yeah, it's a really good question though.
No,
Oh, sorry. I thought it was a technical issue. Okay. So moving on, we're astronomers here. We care about more than just statistics. What I wanted to do is plot out 3 variables that are very well studied with their correlations and whatnot, and see how well my 2 models, my photometry model in the green on the left and my image model in blue on the right, can sort of replicate those correlations in the actual data, which is in the light gray in the background. So what I do, by the way, for full transparency, I create these posterior distributions through sampling, and then I just, for every single galaxy, you sample 1,000 times, you create a posterior, then I find the maximum likelihood value in that posterior, and I treat that as a single scatter plot point in the green and the blue. So what I'm kind of seeing here is that both models kind of replicate the mean, of the center of the correlation, but the image model does a significantly better job at recreating the scatter. You can see it kind of covers the gray a lot better. And just for the sake of visualization, I also made these red rectangles where in each rectangle, you zoom in on it, and those are image model predictions of, like, for example, the top right, you have stellar mass versus metallicity. Those are 3 images that the image model thinks should have a high stellar mass, high metallicity. And then the second row would be low stellar mass, low star formation rate. And the third row would be high SFR, high metallicity. And like just given our visual intuition, it lines up decently well. So can we break the dusty degeneracy? The big question. Nah, not. I mean, it's not great right now. So there are some representative examples in SDSS where you see this is basically what we want to see. And there are a few instances in my test data set where the posterior generated by the image model does a much better job at capturing that direct delta ground truth measurement, I guess, than the photometry model. On the left is a old and not dusty galaxy, and on the right is a young and dusty galaxy. But this is a very cherry-picked example. And we want to see a lot more of this, and we're kind of actively thinking about where we can make improvements right now. So this is the end of like the things that I talked about at AAS. Now I'll quickly talk about what I've been doing since then on this decals DESI data set that I'm using. I'm going to refer to it as the Zoe et al. Catalog to not confuse you, but essentially there's a new catalog that I started using, and the main motivation was that the images were higher quality because it's legacy survey, but it opened up a whole can of worms. So this catalog, what they do is they use 5 broadbands, GRZ, W1, W2 from WISE, and they use 10 artificially created narrow bands that I don't really know much about them, but I'm assuming they're just focusing on like emission lines and whatnot, and fits model spectra through those 15 points and generates the galaxy properties that way. If that makes you feel a little uneasy, I will get back to that. I mean, it's definitely better than standard photometric SED fitting where you have just five broadbands and that's it, but it's also not nearly as good as full spectral fitting. So something I found, which I thought was really interesting, and I found this completely by accident, was that the WISE bands in particular, just the W1 and W2, give us so much leverage for like constraining our properties. The MSE losses coming out of the conditional flow matching model go down by a factor of 2. The posteriors are massively tightened. What I don't mention on the slide is that the delta log P's and actually no, I do mention it because I have these plots on the right where I'm comparing these models that only use 3 bands, just GRZ from DESI, and versus models that use GRZ W1, W2 from DESI, and just doing delta log P and DKL, KL divergence evaluations on them. And at every single turn, just adding the W1 and W2 bands makes a massive difference, which is a cool finding. And just to show this using corner plots, these are examples. It's a little small, sorry about that, but these are examples from the SDSS version that I was just talking about of corner plots. Like the plot that I just showed you was like the bottom right corner of these corner plots. And then if you move to this new Zoe et al. Catalog, that happens. They go down massively. So what's going on here exactly? So this is where I start to get a little confused. But
So before,
yes,
can you go
of course.
back to the previous one?
Yes.
Oh, sorry, one more.
Yes.
So
I did not explain
do
the
you see a big difference in when you condition? Well, just looking at these posteriors of the sample, do you see a big gain when conditioned on both images and photometry with respect to just photometry? In other words,
yes,
those actually very different in terms of the constraining power?
So that's a good question. And I don't know if I actually get to it here, but it's actually a lot worse of an so the improvement from, how do I phrase this? The improvement here is a lot smaller than it was for SDSS, and I think the reason for that is now just the photometry-only model is doing such a good job of capturing those direct deltas that adding the images in doesn't really do much. So that's also something we're thinking about, but I think there's some cases where when you're trying to look at like hard problems like the dust age degeneracy or like other degeneracies where these photometry only model doesn't do as good of a job and misses the mark, those are areas where the image model can actually come in and improve on it. So that's my take for now. Another great question. So yeah. So my theory as to why these posteriors get so much tighter for the DESI version is basically that we have W1 and W2, which are these infrared bands. And if I just took a random black body spectrum picture off of the internet and the GRZ bands are all in like the visible, slightly redder than visible area, whereas W1 and W2 are like off the charts. So basically when you have measurements in these wise bands, you're pinning down the tail of the spectrum. And because you're looking at, like the older stellar populations there, which are really good for pinning down the stellar mass, we can constrain the stellar mass in particular a lot better using just those two bands. And then the kind of more obvious one, I think, is AV, where we have 3 data points that can't see through dust, GRZ, and we have 2 that can see right through the dust. We throw them at the machine learning, which is just a glorified polynomial fitter anyway, and it basically can figure out, oh, if I subtract the 2, I put it in air quotes, I can figure out how much dust there is. So that is my theory for now. Can we break the dust age degeneracy this way? I'm still looking into this in terms of population statistics. One thing I will say, actually, to answer your earlier question, Raphael, I remember I just remembered this. The image model for like these sort of young and dusty galaxies or old and not dusty galaxies improves on the photometry model about like 65-ish% of the time. So it's a lot lower than the 81% that I saw with SDSS. But the good news here is that both models are generally able to nail the ground truth, quote unquote, properties for old and not dusty or young and dusty galaxies a lot better than they were for SDSS. So, oh, and a quick side note, by the way, the kinds of galaxies where my image model tends to completely outperform my photometry model, like do the best, are ones that have color gradients, which is kind of an interesting finding. Ones where like there's like a red, kind of like this one on the top left, which is why I was reminded of that. Ones that have like a reddish yellow bulge in the center and they kind of disperse into blue. The image model tends to pick those up a lot better than the photometry model does. And my advisor actually came out with a paper, I want to say in 2020, that says kind of the same thing, that things like CNNs, for example, have the most success when the galaxies they're looking at have color gradients. Yes.
Are they passed in as RGB JPEGs or as the bits files of GRZ bands? Like the raw data will you process it so it's an RGB JPEG?
Yeah, so for these images, I take the photometry, the GRZ photometry, and I make all these transformations to it that I'm not remembering off the top of my head, and turn them into RGB JPEG images. And then for the SDSS version, they were similarly GRI band false colored into RGB images.
Right.
So, and that's what I'm actually feeding into the model, not just for visualization purposes.
Question about that.
Oh, yes.
So then maybe continuing on that question, does that mean that in the data set where you have access to the WISE bands, does your image model not use WISE images in training? And do you think that if you did,
So it doesn't use WISE. That's a good point. So it doesn't use WISE images. What it uses is so the GRZ images that are false colored that I encode down using a CNN to like 256 dimensions, concatenated onto GRZ W1, W2 photometry. So the only WISE information in there is those two photometric bands. So yeah, it's a good point. Using those instead of feeding the RGB JPEGs in, if I kind of just threw all the photometry in image form, that could make a difference. Yeah.
Yeah.
Yeah, it's a great idea. Yes.
When you say that stuff like a color gradient helps your model to outperform, have you looked at stuff like saliency maps or local like line explorers, stuff like this?
I should. Yeah, it's a great idea. So I can target exactly what it's looking at when that happens.
Yeah.
That's a great idea. Yeah. See it.
I was wondering what's your expectation for redshift? Are these like super low for galaxies, relatively local, or do you expect some amount of redshift?
So my redshift range is about 0.02 to 0.31-ish. So they're local enough that I'm not worried about redshift effects, but yes.
Quick follow-up. So for the WISE band, you said it was a 3.4 micron, and that's correlated with like a pretty large dust emission feature from polycyclic aromatic hydrocarbon. I was just wondering if, I don't know, if you've thought about that or
No, I have not. Yeah,
if that's like
good point.
picking it up, it's like the actual presence of heat of dust.
Oh yeah. Yeah, that's a good point. Thank you for that. Yeah. Yeah, cool. Awesome. A lot to think about.
Want me to take notes?
Yeah, I'm right after this, I'm gonna go straight back to my visitor office and jot all this down before I forget it. So what I'm doing now is I'm basically doing the same thing, exactly the same thing, but now I'm using a third catalog. So instead, made a quick side note earlier, which is that the fact that in Zoe et al. You're getting all these galaxy properties just from 15 bands. I mean, it's better than photometric STD fitting, but ideally I would have spectra that I'm using. So I'm using this new data set that fast spec fit where you have the spectra and also GRZ W1, W2, W3, W4 bands, and you're doing the fitting that way. So this is because I'm a lot happier to call that a close to ground truth, like target variable, than what I was using previously. So the thing that really befuddles me, especially after all this conversation about W1, W2, and whatnot, is the losses now go back up to what they were in the SDSS version. And this is work that I did like literally last week, so I need to look and see, make sure there's no bug anywhere. But my current theory for why it's happening, unless it's a bug, obviously, is that maybe I mean, with W1 and W2, those are two of 15 bands that I'm using in the Zoe et al. Catalog, whereas here you have all the data from the entire spectrum. So I'm guessing that the derived properties are more dependent on the spectra than on the photometry. So there's a chance they're getting drowned out. And an idea that I had is to like weight the WISE bands a lot higher and see if that makes a difference or if there's something else going on here. So to conclude, just some takeaways. This is, by the way, the SDSS paper that I put on archive back in December. But so in our like methodological CFM setup, I do think that at all turns, images do provide useful morphological information. Sometimes it is marginal, like in the DESI case, the Zoe et al. Case, for example, but it does always improve in some way, shape, or form. Images move the posterior between DN4000 and AV or Asian AV, whatever you want to say, towards a spectroscopic target, but obviously it's a really hard problem to solve. I think we're making progress, but it's going to take a lot more work before you get there. And then yeah, what I said about W1, W2 being very important bands, I still believe that. And there's a lot more investigation to do with this new fast spec fit data set, but yeah, that's it for me. I'm happy to take any more questions. Thank you so much.
Well, thank you, Mikaeel, for a nice talk. Oh, you made it. All right, questions? Dan, do you have a question?
Yeah. What fraction of these objects do you have spectra?
So for
targets, right?
yes, so for SDSS, so right now I don't have the actual spectra, but I like theoretically I could go and get them for SDSS and for fast spec fit. I don't think the Zoe at all has them, but yeah, I could go and get them theoretically. Because it'd be useful, I think, to actually do the fitting myself.
Right.
Yeah.
I'm just wondering if you could learn something from the spectra.
Yeah.
Right, correctly.
Yeah.
Betting.
Yeah. It's a good idea, and it's kind of I know AstroClip kind of does something like that, and I need to reread the paper to remember what they're doing. But joint embeddings with spectra are a really popular thing to do, and I think you can learn a lot from doing something like that. So it's a great idea.
I make sure I understood the issue in the previous slide.
Yeah.
Okay, so you said that when you go to this data set, you have
Yes.
many more bands. And then doing all of this training on that, your losses go up. Thank you.
So not only many more bands, but also like I think it's fitting directly on the spectra rather than just looking at a bunch of bands and fitting that way like so it all did. So my theory is that the W1 and W2 are getting like drowned out essentially. Still yet to confirm it, but yes.
How many data points do you have with this?
Across the board in all three data sets, order like 100,000 total. So then I train on like 80,000, test on 10,000, something like that. Ideally I'd have more, but I think I'm currently limited by my images, funnily enough. Because yeah, I don't really know why, but that's what's limiting it.
So it's the same amount of data that you're training this on than the previous one.
It's slightly less, but like it's like 10,000 less. It's not so much less that I'm like concerned about that. Yeah,
No,
maybe I should be. I don't know.
you think the dimensionality a lot of your constraint
Yeah.
factor, right? Because it went from like 5 to however many.
Yeah,
So it might just be like harder to learn from it, and
because I need more data.
to overfit, right? It's
Yeah.
basically like you have an ID for each image.
Yes.
Good point. But yeah, that's part of it.
I would love more data. Yeah. So let's see if there's anything I can do about that. But yeah, it's a good point. Yes.
What happens to outliers? I'm wondering about
Yes.
galaxies that might be overly, unusually large for their given mass, or something weird like a galaxy merger.
I was about to say mergers. So yeah, for those, I think those are actually my most popular failure modes, where my photometry model actually does better than my image model. For obvious reasons, so I'm just passing an image and it doesn't really know what galaxy it's looking at. Another popular failure mode is like those really nebulous dwarf galaxies where I think there's just not enough light in there to actually for the image to actually like learn anything, I guess. And even with like the background noise, that there's a little bit of RGB fluctuation, so it kind of just doesn't really do anything. But those are my favorite, well, I guess least favorite outliers depending on your perspective, but most interesting, I guess. Yeah, and then I guess another type of outlier on the other side of the spectrum is what I was saying about the color gradients. That those are the ones where the image model like destroys the photometry model. Yeah.
So conceptually, the photometry points are just some sort of summary from the images, right? In that
Yeah,
you take photometry from the image.
basically, yeah.
And so I think what, I mean, very conceptually, I guess what the relevant question, one of the relevant questions here could be, what is it that the image, what sort of summaries you can create from the image that actually enhance the amount of information you have? So I'm just thinking out loud here, but a concrete question, are you surprised by any parameter that you can constrain better when you add the images with respect to so what is it that the images are really giving you in terms of constraining parameters? Did you expect something like the star formation rate to be more informed because of the spiral arms or whatever? And is that the case? Was there anything that surprised you in that?
Yeah, so I mean, the first thing that's coming to mind when you say that is this scatter plot that I made, where it seems to just get the sort of spread in galaxy properties a lot better for, I think that the three were that it does the best at. Actually, no, I'd say the two that it does the best at are stellar mass and star formation rate. Metallicity, it's a little worse at, and then as you go into things like age, and it's kind of the thing where like the harder, how do I say this? The harder the problem is, according to astronomers, the harder it is for my machine learning stuff to target those kinds of variables, which I think makes intuitive sense to me. But I think the two that it gets the most reliably are stellar mass and star formation rate, because of things like, a more blue, like a blue spiral galaxy is probably going to be forming stars, and a red and dead elliptical galaxy is not going to be forming stars. So it picks up on things like that really well, I think. Yeah.
I'm glad the machines are still not doing better than us. Personally.
Yeah, me too.
Some additional spectroscopic things that could be interesting. It could be interesting to target would be things like, the velocity dispersion. Things that you measure from the spectrum only. How much?
Yeah.
How that relates to the mass of the central black hole. These are things that we should chat about.
Yeah, absolutely.
All right. Any other?
Very dumb question.
Yeah, such thing.
So you're showing the blue galaxies on the center panel here, and are you saying that those are the ones with low stellar mass and low star formation rate?
That my image model thinks have low stellar mass and low star formation rate. So I'm basically making this, I'll use my mouse so people online can see. I'm putting a red rectangle right here, and I'm selecting some of the blue points that my image model, I guess my sort of point in showing these images is being like, my image model is selecting galaxies that kind of visually make sense to us, essentially.
This is me just being not thinking about galaxies as individual sources of this and not, but why are they blue then?
Oh, so
It's this is a bit awkward question. I can ask.
yeah, we can talk.
I just thought if there was an easy answer, or maybe that one I didn't understand. I don't.
Okay, maybe we can chat about it.
Ages of the stellar relations.
Yeah, but if they're blue, I would expect them to be really young.
Right.
High star formation, so I guess, I don't know.
I mean, I do see, maybe these are, they could be better images, but I do also see things like edge-on spirals, or not edge-on, because then I don't know if it's a spiral, but like discs and stuff, and these kind of things. So yeah, but yeah, that I kind of had the same evaluation, that it's like a young stellar population.
Still so covered by dust. I don't know.
Yeah, we could chat about this. It's a good question.
So it's the bar over stellar mass that matters, right? To give you specific star formation rate.
Shoot, yeah, see, I work with result stars, so.
Yeah, I should probably switch to using that. That's a good point.
Okay, well, looks like that's
Anyone
it.
online?
Oh, yeah.
Yeah, any questions online? I would love to.
Any questions online? If you do have a question, you can just unmute yourself and ask. It doesn't look like it. So, well, with that, let's thank Mikaeel again. Thank you very much.